Hi, welcome to my talk, Know Your AAV Inside Out, Answers from Quantification to Stability with Stunner, Uncle, and Big Tuna. You know the feeling where you just want a late night snack, so you start to fantasize what to eat, but when you check the fridge, there's less there than you hoped. AAV production seems a bit the same way. You get enthusiastic about all the things you can achieve with your AAV sample, just to realize at the end of the road that your sample is not as good as you want. That is exactly where Unchained Labs can help, so you can always know your AAV inside out. When characterizing AAV, you have a lot of things going on. It's important to know how much protein is present, how much DNA is present, if things are intact, if they're the right size, and if there's any aggregation. It's a truly complex biologic that demands a lot from characterization techniques. That is why characterization of AAV is a very broad subject, and it's still evolving. For every one of these needs, there are many technologies trying to meet the need. Today, I'll show you how Stunner can help address the needs shown in green, that is titers for full capsids and total capsids, the empty-full ratio, and if there's aggregation going on in an AAV sample. Now, let's focus in on two technologies, DLS and UVVIS. Each of them tells a part of the story. DLS gets you info on capsid titer and aggregation, but can't say anything about what's happening with DNA. On the other hand, UVVIS gets you the total amount of protein, DNA, and can link those to an empty-full ratio, but doesn't give you info about if any of this is contained in capsids. Each gets valuable info, but neither tells you everything. So what if you could combine them to get a whole story? That's where Stunner brings it all together, to deliver answers on capsid titer, empty-full ratio, and aggregation with only 2 microliter of sample in less than a minute. And there's no labels, no reagents or standards. You just use the sample you've got. Now, how does Stunner do this? Simply add in 2 microliter of AAV above a titer of 10 to the 12 into the input well, and it's pulled into the microfluidic reservoir. At this step, the sample can sit for up to 2 hours before reading, with no evaporation. After the plate is loaded into the instrument, the circuit is read first when empty, that removes any absorbance contribution from the plastic, and then a pump applies a small vacuum, which moves the sample into the microcuvette to be read. Because the circuit has fixed path lengths, it can make very precise and accurate reads. Stunner contains 2 technologies to read each sample, UVVIS for concentration and DLS for sizing. SLS intensity data is also read during a DLS experiment, and samples can be read from 1 to 96 samples at a time. Stunner's AAV quant application will combine all the pieces of information into the full story about your AAV. Checking out your AAV with DLS tells you what shape your sample is in, if there's only capsids or if aggregates have started to ruin things. DLS also lets you figure out how much SLS intensity is coming from just AAV capsids. That's just the green peak on the left, while the gray peak is aggregates and larger stuff. UVVIS brings information on how much total protein is in your sample and how much single-stranded DNA there is. Based on some simple info you tell Stunner before an experiment, it calculates empty-full ratio and percent full for you. What Stunner is doing is shown step by step here. First, DLS identifies the capsids, the aggregates, and how intense the signal is from each of those populations. In the middle, that info then helps you split up your SLS signal from a total into the amount just attributable to empty and full capsids combined. And finally, UVVIS brings in that info about empty-full ratio plus protein and DNA totals to provide the last piece of the puzzle. Now here's the whole story told in one graph, starting with the left side blue bar, which is the protein in a sample. UVVIS got you the total amount of protein, and here we're expressing it as how many possible capsids all that protein could make. By adding in DLS and SLS info, Stunner splits up that information into the light blue bar, which is the aggregates and extra protein chunk, and the dark blue bar, which is the total titer for the AAV capsids. On the right-hand side, in the green bar, the process follows the same steps for DNA. The total height of the green bar is the total amount of DNA expressed as the total number of viral genomes that you can make. Light green is extra DNA, and dark green is the number of full AAV capsids. Dividing dark green by dark blue, so the full capsids by the total capsids, gets you its percent full number that we also convert into empty full ratio for you. Now here's that same data showing you Stunner helps you know your AAV inside out. Dark green divided by dark blue is percent full, and this is shown in yellow. Purple is percent empty, which is just the remainder. Empty full ratio is percent empty divided by percent full, so purple divided by yellow. And if your preferred term is CP per VG ratio, that will be the inverse of the percent full number. Now, if you try to fake out Stunner, here's what happens. In this case, we tried out two samples, one with a mixture of IgG and DNA to simulate full capsids, and another one with just IgG to simulate empty capsids. Stunner knew what was there and wasn't fooled. On the left, Stunner says almost all the IgG and DNA is free and aggregated protein or free and aggregated DNA, and the story is similar on the right. To look more into our ability to see percent full values, we took stocks of empty and full AAV9 and mixed them at different ratios. For each combination, 100% full stock and 80% full stock and so on, Stunner gets a good read on the data, and percent full and empty align well with expected values. And this idea works for any serotype. Just tell Stunner the basics about what serotype you have and what is its DNA payload, and Stunner takes care of the rest of the heavy calculating. For getting a capsid titer, Stunner is way faster and requires less upfront work than ELISA's. Here we've taken full or empty AAV9 and ran a dilution series where we've compared Stunner's total capsid titer metric against the results for a capsid ELISA. The results have slopes close to 1 and R-squared values above 0.99. And importantly, it would take hours to get this ELISA data, while Stunner's done it in less than an hour with no sample prep. From only 2 microliter, Stunner combines UV-Vis, DLS, and SLS data to tell the whole story about your AAV, delivering mountains of data about sample aggregation, AAV full and empty capsid titers, and an empty full ratio. So that's how Stunner delivers label-free, standard-free, and hassle-free gene therapy quant. But Stunner is not the only system in the Unchained Labs gene therapy squad. I want to introduce you to 2 of our other systems, Uncle and Big Tuna. Uncle is an all-in-one multimodal stability platform built for biologics. It uses 2 lasers to excite either label-free protein intrinsic fluorescence or a variety of dye-based fluorescence. With full spectrum fluorescence detection, Uncle can pick up both kinds of signals. Today, we're going to be looking a lot more into Uncle's full spectrum fluorescence with a fluorescent dye sensitive to DNA, and by looking at the fluorescence of the native protein of AAV capsids. SLS is the scattered light from those 2 lasers, and it gives information on when aggregates form. DLS is the dynamic light scattering system and allows for detailed measurements of size and size distribution. These 3 detection methods can be operated isothermally at room temperature or across a heat ramp designed to thermally stress samples and see which ones can take the heat. Uncle is able to deliver results on aggregation and 2 different looks at viral capsid stability in about 2 hours with 9 microliters of sample for up to 48 samples at a time. From Uncle data and the academic literature, we can see these 2 behaviors happen at different temperatures, with genome ejection actually occurring at temperatures far below capsid disruption. This is why measuring viral stability on the Uncle is so important. It can look at both of these pieces of data and aggregation data too. Now here's a look at the analysis for the Cyber Gold fluorescence experiment. In green, we'll be looking at the fluorescence of the Cyber Gold dye, and we'll be tracking the area under the curve. In blue, we have the SLS of the 473 nanometer laser. So starting at 25 degrees, we see some initial fluorescence signal from cyber gold because we know that we have some free-floating DNA present in the sample. As temperature increases, cyber gold fluorescence decreases because we know there's a relationship between temperature and cyber gold fluorescence. However, the headline of this experiment is starting at 50 degrees when we begin to see cyber gold fluorescence signal increasing, indicating that genome injection is beginning to occur from our AAV capsid. We've also identified an inflection point at 58 degrees, which what we'll use to compare different genome injection curves across serotypes and different formulation buffers. This genome injection behavior continues until approximately 75 degrees Celsius, where we again see our SLS signal spike, indicating that aggregation is occurring in our sample. Because we've also looked at the intrinsic fluorescence data, we know that aggregation, unfolding, and capsid disruption are all tied together for this AAV sample. In this case, we're looking at 10 to the 13 Vg per ml AAV9, but we know that Uncle can measure from 5 times 10 to the 11th all the way up to and beyond 1 times 10 to the 14 Vg per ml AAV using cyber gold dye. So that's a look at how we can see more AAV stability behavior with Uncle. Using Uncle's 2 lasers and full spectrum fluorescence, we're able to look at both pathways of AAV stability, the genome ejection and the capsid disruption pathway. ZLS was able to look at sample quality before a thermal ramp and is another quantitative measure of aggregation. And its particle intensity and cyber gold fluorescence metrics are useful tools to look at capsid count and DNA on the same sample. And importantly, most of this information actually is available in only one experiment using only 1 9 microliter volume of sample. And lastly, we have Big Tuna. Big Tuna is an automated buffer exchange platform to help you clean up and concentrate your AAV samples. Big Tuna uses a combination of pressure-based ultrafiltration and diafiltration and orbital mixing to buffer exchange. It can handle sample volumes as low as 100 microliters and up to 8 milliliters. It is an easy, gentle system with minimal hands-on time unless you walk away once the experiment has started. Everybody needs to do buffer exchange, but unfortunately, most of the development work buffer exchange are still very manual. Take dialysis, for example, here. You have to use a ton of buffer and take a long time to finish buffer exchange. Transfer the samples into centrifugation device again in order to concentrate into the right working range. The process is laborious and tedious. This is where Big Tuna can help in automating the entire process of buffer exchange and concentrate your sample into the right range in one step. You place your samples in our unfiltered plate. Big Tuna will measure the sample volume with acoustic volume sensor and apply positive pressure to remove filtrate. After the filtrate is removed, Big Tuna will automatically add new buffers. The cycle of removing old buffer and adding new buffers will continue a couple of cycles until all the buffers in the wells are displaced. This is all hands-off. So make sure you know what you have, so when you have a craving, you can get exactly what you want. I'll take any questions now.